Okay, so let's begin. Thank you.
Yeah, thank you very much for this kind introduction and also for having me here at Leeds, Loughborough, Nottingham, and Munich simultaneously, right? So it's really a great pleasure to give this talk today. So today I'd like to talk about this anomalous transport in constrained quantum matter, and I think during the talk it will become more clear what I mean with these words. I'd like to point out at that point that this project which I'm going to present have been pushed forward by Johannes Feldmeier and by Sala, who are PhD students in my group, and also by Giuseppe, the Tomasi, and Frank. So when you think about a quantum many-body system which is driven far out of equilibrium, then on the first sight you might think it's a real...
The result of doing this recently is also something interesting, that if you deliberately, we then did the scaling of all these members.
So maybe this is not intended for us, right?
Yes, yeah, I just mute them, sorry, yes.
No worries. So I just wanted to say that when you think about the quantum many-body system out of equilibrium, then on the first sight, you might really think it's a total mess, right? Because we can't apply directly our techniques, which we know from condensed matter physics or from statistical physics for equilibrium phases in general. But rather, we would need to have to invent new techniques and think about new concepts. So, however, luckily, there are a couple of universal guiding principles which help us to understand some basic effects in non-equilibrium quantum dynamics. So think of a quantum system which has some extensive conserved quantities, for instance, energy, charge, or spin. Then when you look at the relaxation dynamic of a typical state, you might start out with something which has a lot of fluctuations. And then initially, at short times, there happens some fast relaxation due to local equilibration. And this local equilibration is of pure progresses. It's not so easy because they cannot relax via local processes anymore, but rather very slowly, collectively via transport. And so this process, however, to have an emergent transport in terms of a microscopic Hamiltonian is a very complex one, right? Hop of my particle between nearest neighbors, and typical Hamiltonians are just Hamiltonians with compact support. So the question which one can ask, even though this is the expectation, right? So that first, at short times, we have some quantum evolution, very fast, local relaxation by local equilibrium. At late times, we will have this diminishing of long wavelength excitations. I mean, how can we capture this full span in the time evolution? I mean, this was is an open question in the field in some sense, and people have developed different techniques ranging from numerical ones, which I'm highlighting here. So for instance, you might think of representing a quantum many-body state of a low-dimensional system with a matrix product state, and then evolve this in time and calculate, for instance, correlation functions out of that. And what we want to span in some sense is this regime from the very shortest times where quantum mechanics matter to the very longest times where there's an emergent hydrodynamics. And by now, 5 years back, we have tried this on the Bose-Hubbard model. So this has been done by a student of mine, Annabelle, and Christian Mendel, and Manuel Endres and myself. So we have looked at the Bose-Hubbard model, and we wanted to calculate density-density correlation functions in the system from a pure quantum mechanical perspective. And we wanted to see whether we can reach really this emergent hydrodynamic regime. And this is precisely done with some tensor network techniques, so we have control on the numerical accuracy. And you see, for high temperatures, we nicely see a 1 over square root in time behavior of the autocorrelation function. So this is what we calculate is density excitation at site 0 in the middle of the system, and then we ask how much of this excitation has revived at later times. And you know, in this system, we have a conserved total density. So effectively, the density undergoes the effective hydrodynamics of that description is just a diffusion equation. So if the time derivative of the density is equal to the second derivative of the density, and the prefactor is the diffusion constant. So we do know from our undergraduate physics studies that when we solve this equation with a delta initial condition, which corresponds to this density correlation function effectively, then we get a Gaussian out. The Gaussian solves this equation with a standard deviation which increases as a square root in time. Or when we look at the autocorrelation, then this exponential of the Gaussian just goes away, and I have 1 over the standard deviation in front. So I have 1 over square root in time. So whenever we have something like this, this is a signature of diffusion. Right? Turns out that in that model, it's actually a bit more tricky because the Bose-Hubbard model in 1 dimension is integrable. So when we look at very low temperatures, what we have is we have sound modes which are propagating ballistically through the system, and we mainly see a 1 over t decay of the autocorrelations, and only at much later times hydrodynamics would kick in, but this is a time scale beyond reach in our numerical simulations. Okay, and maybe in case this emergent hydrodynamics is of such systems is of interest to you, recently also we have collaborated with Rainer Platz's group in Innsbruck. They have a trapped ion quantum simulator, a quantum computer, and in that experiment we could also bridge the regime, the shortest regime from quantum evolution down to the latest regime where we see an emergent hydrodynamics in the long range trapped ion model. So this can be found in that work. But anyway, I mean, we have now some guiding principles at our disposal, right? So, which I call the universal, because, you know, when you have conserved quantities, we expect that there is some emergent hydrodynamics at late times, which is diffusive. So in localized excitation at time 0 would just spread as square root in time. We also have another notion of dynamics, where we know very much about it, which is the growth of operators in a quantum system. Operators grow ballistically, because the idea is just in some sense that whenever I apply a time evolution operator, then this is not commuting with my initial excited operator here in the system. So whenever I apply such a commutator, I will pick up a little bit more extent. So there will be this ballistic growth. So in those two principles can be argued on very generic grounds. So they are in some sense universal aspects of non-equilibrium quantum dynamics. Are there any questions at this point? So please, as I said in the beginning, I would be very happy to receive many questions during the talk and stop early in some sense. So what I want to cover...
I have a question here. So could you also define particular operators which have diffusive growth? Is that possible?
Yeah, okay.
Is that a matter of which operators you choose? Yeah. So.
In general, no. There are just some exceptions that when you take particular states, for instance, you know, what has been found out is that operator growth is also described by an effective hydrodynamic description with a biased random walk. So this picture is very generic, and one has to work hard actually to find exceptions to this rule. So maybe let me answer this in that way. It's a bit vague. We can deepen this discussion a bit more. I mean, there are indeed some subtleties which we can talk about. But my point today is really to find more generic exceptions to this rule, right? And what I want to advocate is that this so-called, what I call constrained quantum systems, they provide a nice playground to us where we find exceptions to this generic behavior, which is still robust and universal. Okay, so let me explain to you the system which I have in mind. So I am thinking about a constrained quantum system which has two conservation laws, charge and dipole moment. So I write this in terms of a spin language. So conserved charge means just total conserved magnetization of the system. So the sum over spin is equal to a sum magnetization, Q. And dipole moment means position times density operator, sum over it is conserved. So this is n minus SNZ is a conserved quantity. Okay, so these are the two conservation laws which we consider, and we don't need to necessarily consider anymore, just these two. And why do I call it constrained, right? This is in some sense, I mean, sounds a bit like a miracle at the moment. So let's consider a system. I don't even define a Hamiltonian at that point, right? I just impose those two rules. And I tell you that we consider a Hilbert space with three local states. This could be a spin 1 Hilbert space, spin pointing down, I draw a minus, spin somewhere in the plane, I draw a 0, and spin pointing up, or the three spin 1 states, spin pointing up would be a plus here in this notation which I have, right? I have a local Hilbert space with these three states. And now let's look at the very simplest problem which we can think about. When we just have charge conservation and we think about a charge excitation on top of a oppositely polarized background, then this charge can undergo a random walk on top of this background and would just diffuse out, right? If I have generic interactions, I'm not thinking about a quantum walk, a non-interacting one, then you would get ballistic propagation, but it would propagate out. So what is happening here? Actually, due to the dipole conservation, or let's write down the quantum numbers first of this problem. So charge is +1, dipole moment is 0, because I essentially have no charges here and only a charge in the center. So, but this I multiply with position 0 essentially. So dipole moment is 0 of the system. When now this plus particle wants to hop one step to the right, charge would be conserved, of course, but dipole moment is not. The dipole moment unit would change. So I cannot make this transformation. What I can do instead, so a single plus does not move, but what I can do is a plus can move to the right and simultaneously emit a dipole to the left. Okay, so let's check it out. The charge is still +1 and the dipole moment is still 0 because this charge cancels out with that one. And now the dipole object, the dipole can move away from the system, but the plus charge is again stuck until it emits another dipole. And so this is the consequence of charge and dipole conservation. And recently, people have been discussing this also in the language of fractons. So fractons are systems which have quasi-particle excitations with constrained mobility. In one dimension, that just means that they are stuck. In my case, this plus is a fracton particle, it's stuck. It can only move when it emits a more complex other object, which is a dipole in that case. And this is precisely these characteristics of these fractonic quantum systems. Okay, so here maybe we have something like a fracton in one dimensions. So the simplest thing you can think about if you want. Okay, good. So we have this prescription, and now let me think a little bit about the or also recap a little bit about the physics of these systems. So on the one hand, when I have now a typical state, which consists now of blue, red, and white dots, then individual particles may not be able to move, but the dipole can come by, can then facilitate some new moves and so on. So there is motion. So it's not completely stuck, right, the system. The dynamics is just a bit unconventional. So we can't think of it as simple particles moving around, but you have to emit things, absorb things, and then motion can happen. And indeed, when you look at the autocorrelation function of the system, we see something like this, that an excitation decays slowly over time. But the question is now, what is this hydrodynamics of that system? Is it just diffusion, the one which I've educated before, or is it more complicated, complex, or exotic, or interesting, if you want? So this is the, excuse me, this is the generic behavior of this system. But now there's another ingredient which we have. So we can tune the average particle density in the system. Just think that we have a canonical or even a chemical potential, grand canonical ensemble, where we can tune the typical particle density. When we are in a regime where the average charge is very big, then I can't find these recombination processes. And at some point, my system is really stuck instead. And it turns out that for charges which are above an critical charge, the system is kind of localizing, but not due to disorder in the system, but really due to the constraint which is imposed by this conservation law. And it turns out that the Hilbert space of the system in that regime is fragmented. It's fragmented in exponentially many sectors, and this is what we called Hilbert space fragmentation. This is what Pablo and Tibor and also Ruben have worked out in a paper a couple of years back. But right, today I want to, this is the general picture of this system, and there's a critical point separating this ergodic phase of fractonic quantum matter from the localized phase of fractons. And there's a critical point in between, which has been working out by Alan Morningstar and David Hughes and others. So one knows that there is this transition point. So this says, yes.
So the fragmentation is independent of Q, right?
Here it's a bit trickier. So it's in our model, how we came up with fragmentation, it's a bit in a different context. There we didn't tune the charge and find fragmentation, but rather what we did is we wrote down certain models where the whole Hilbert space is strongly fragmented. Okay.
Right. So it exists for any Q, but it becomes more dramatic when Q is large, right?
Right.
Smaller sectors,
right. It becomes more dramatic when Q is large. So we cross over to something like which we called a strong fragmentation, where the system really localizes. So autocorrelation functions would not decay because I have exponentially many sectors. And when I search or when I select an initial state, which is, for instance, in this sector S here, it can never go out. So the relaxation is just within this block essentially.
But some of the sectors are still exponentially large, right?
Right, but exponentially smaller than the total Hilbert space. So the fraction of the maximal, there are various cases which you can cook up. In this case of absence of thermalization, what happens is that the largest sector in my Hilbert space divided by the total Hilbert space dimension given a charge and dipole quantum number, this goes down exponentially to 0.
Right, but I guess my question is, you're saying there is localization. So if the largest sector is still exponentially big, why is there localization?
Well, but still, the question is just the dependence, the relative dependence between. Yeah, okay, good. The question is, where does the right? So, what is your average which you're taking over, right? So when we average over the whole infinite temperature ensemble within a certain fixed Q and P, then there will be exponentially many sectors also which don't relax at all. So this is this interplay which you have to consider.
So the average is dominated by small sectors.
No, the average is right. The average is dominated not by the largest sectors, but somewhere in between. This can give you the localization essentially. We've refined pictures of that too, so you can write down actually for the system which we have considered back then. This is now a spin 1 system with the smallest support which you can think about, 3 sites. There we can even write down all the labels which label these sectors of the Hilbert space, and there we can work out essentially all the ratios explicitly and so on and so forth. But here all those details don't matter so much. For this talk today, it's just important that we have even though there is no quench disorder in the system, we have a regime here where for low average charge, where the system is effectively ergodic and relaxing, and there is a phase transition toward a regime which is non-ergodic. This is so unfortunately I don't have enough time to tell you all the full story on the right-hand side here of the picture, which maybe Pablo is going to do in a couple of weeks because that's his main contribution. So I hope, Sarko, is this kind of, yeah, satisfactorily answering the question. Good. Yes, so that's the picture, and it sets the scene for the talks. Are there further questions on that?
Following on Slatko's, just a point of clarification, or so nothing that you're saying here is quantum. Yeah. So this could be, this also happens and has been studied a lot in classical stochastics. Is what you call fragmentation is the reducibility or not of the dynamics.
And we will use actually some language even from which you are very used to from a classical community to understand a bit what is going on in this system.
So all I want to say is that ergodicity and reducibility are two slightly different things, in the sense that you're not just non-ergodic because you are reducible, you fragment. You might have a dynamically connected sector, like your box, your box S, and exploring all the configurations that are dynamically connected might take infinite time in the large size limit and so on. So these are two questions that shouldn't be confused. I'm just making sure that we're, we agree.
Yes, we fully agree.
Okay, thanks.
Right. So that will also be in some sense the beauty, I hope, of what I'm going to show. I mean, what I'm telling you is that we find universal laws out of this quantum mechanical, which are emergent laws, which are, however, effective classical laws. Right? Just to put it a bit in different words, maybe what Juan has also said. Okay, good. Now, first step is we focus on this side of the where we do have relaxing autocorrelation functions. Okay, so as I said, typical hydrodynamics with just charge conservation, we get a diffusion equation out with what is called in the community dynamical exponent z is equal to 2. This is the relation between time and space. Okay, so this factor z here it gives you z. Turns out that when we look at dipole conservation, then this leading term cannot contribute, but the first leading term which we have is actually a fourth derivative. So the dynamical exponent of this system is actually 4. So we get very slow dynamics. So it takes long, the fourth root in time, essentially to spread a little bit of length. So this is subdiffusive dynamics, which is happening here. So when we look now at our density profile, how it should look like is that the spread here goes with a fourth root, and also it should decay as a fourth root. And the function which we get out of this equation is also not a Gaussian, but it's a dress type of geometrical function. We can work it out, but it has a bit of like wiggles on top if you want. So this has been worked out by Johannes and Pablo in this work from last year, and simultaneously actually Gromov and Andy Lucas and others have also a paper deriving analytically the same hydro equations. We have also some numerical results on top. So how do we think about this emergent hydrodynamics? The derivation is very simple. So we write down the Heisenberg equations of motion from a Z operator. And what we get is that it's the second derivative of a dipole current. We then take the long wavelength limit, which means that we take expectation values in this system and look at the dominating contributions. So we pull the expectation values in, if you want. And the hydrodynamic assumption now is that we can make a gradient expansion for the current. So we will have a lowest order beta in our gradient expansion, which acts. So normally this is in analogon to the fixed law of diffusion, right? So you say current is minus gradient density, but we don't know yet which is the power here, which we have to plug in, and some higher derivatives. And in the long wavelength limit, the higher derivatives we can just discard. So how do we fix this power? We assume that in equilibrium, we don't have any currents, okay? And so the current has to vanish. But how many conservation laws do I have? I have 2 conservation laws to fulfill, charge and dipole moment. So that means that I have to take the second derivative essentially. So I have 2 free parameters to fix this equilibrium current. So beta is 2 in our case because of these 2 free parameters which we have to do 2 conserved moments of the system. So that means when we plug this in, the current goes as the second derivative of Z. When we plug this back in, you see we have the fourth derivative. And this is how this hydrodynamic can be worked out. And then, okay, you have to be careful. You have to look at all possible combinations which can possibly happen and look at something like in a randomization group sense, which are the dominating terms, but all the other terms are actually higher order. So I don't talk about them here in details. But if you want, you can have a look at this, at our paper. We work it out in more detail there. So this is the hydro equation of fractons, if you want, in one dimensions. Okay. So now, how can we verify this a little bit better? And this now goes into the direction of what Juan has just asked. Turns out, since this is emergent classical dynamics, we can use classical cellular automaton to mimic the time evolution. The only place where quantum mechanics enters is in the value of this diffusion constant here. This depends on microscopics, but the rest is long wavelength physics, which should uniformly and universally emerge for our system. Okay. So what we do is we write down a couple of gates which conserve charge and dipole moment, and then evaluate correlation functions in this gate, in these evolved gates. So we sample over initial states, sample over gates, and then evaluate the correlation function out of it. But it's particularly easy here because when we look at the ZZ correlation function, sorry, this is now SZ in my previous notation, then the initial operator just acts trivially on a product state. It's just some number, 0, -1, or +1. So we can just evaluate the time evolution of this of the configuration and evaluate at a different position my sigma Z operator and calculate correlation functions out of that. So when we do that, we can confirm our prediction from before. So I said that in the steady state, the density, if I require my dipole current to be constant in the steady state, this means that I have to take two derivatives of the density until it vanishes. So what we can do is we prepare a crazy initial configuration like this, let it evolve under this time evolution and see what the steady state profile is. And indeed, the steady state profile is a linear function. So first derivative is constant, only the second derivative is 0. Okay, consistent with our assumption from before. And then we can also calculate the full correlation function shown on the left hand side. And we do see indeed this functional form which I show you. So we rescale space by the fourth root of time, the correlation function with the fourth root of time. This should give me a scaling collapse of my hydrodynamic equations, and we nicely see the scaling collapse and the functional form of our hydrodynamics emerging. Okay. And now the point is, it doesn't matter whether I do quantum evolution or this effective classical evolution, because I get the same out in the end, right? Because late time, the quantum dynamics is governed by conservation laws, is governed by the long wavelength physics, is precisely governed by this type of process.
Question.
Yes.
So it looks like you need very few assumptions, right?
Yes.
You have conservation of charge and of this dipole moment.
Yes.
I guess you must have some concept of locality in your dynamics.
Oh yes, sorry. So we have gates which have a finite extent in the thermodynamic limit. So I'm not allowed to spread infinity across my system.
I seem to remember when this paper appeared that if the gates were only 3 across, not 4 across, there was an issue.
We had 3, 4, 5 different numbers. It's all universal.
Okay, so as long as you have local gate,
I'm not allowed to scale the gate size with the system size. As soon as I don't do that, then this is the universal scope.
Okay, so as long as you have local gates and you conserve these two, these two quantities, you're saying that these long wavelength description should be like this. Okay, nice. Thanks.
It's very generic. Thanks. You may ask, okay, can we do quantum? Can we add a little bit quantum to the description? And this is actually what Ansgar, a master student of mine, did. So he was developing a non-equilibrium quantum field theory, which takes into account interaction effects. But again, we get the same picture. Look at the density excitation. We get a crossover from a quantum evolution, so we can calculate the short time evolution exactly, to a perfect fourth root in time decay of this correlation, even in the presence of quantum effects. The only thing which changes is the diffusion constant. One curiosity, which we actually, why we developed the method in the first place here, is that now I have a Hamiltonian, actually, I have energy conservation, right? Previously I had gates, random structures. There's no energy conservation in the previous classical evolution, which I showed you. Here we do have energy conservation also. So our hydro theory gets modified, and not only have this one mode stemming from charge dipole conservation, but I have a second mode stemming from energy conservation. And we wanted to understand essentially how this all comes about. And this is, I mean, we hope we finish it in the next couple of weeks. In some sense, it's interesting, right? Because you can think about effects like what is Onsaga relations in these coupled hydrodynamics and so on and so forth. But just for the energy, what comes out is for a generic energy excitation, we see at short times diffusive decay and at late times subdiffusive decay of the energy. That is because energy is typically coupled to charge. If I create, on the other hand, a completely decoupled energy excitation on top of no charge excitation, I can do that by temperature. Then I see diffusive decay throughout. This is the hydrodynamics of this system, and it mixes essentially fourth and second derivatives.
Sorry, I'm a bit confused. So what model are we doing here?
So again, I have not even specified it. So the model which we have cooked up here is again the model with charge and dipole conservation, but I'm considering here bosons for simplicity of the, but just due to technical reasons, because it's hard to write down field theories for spins and for fermions is also a bit tricky. I mean, you can do it, we did it, but not for this problem. So bosons. So
some kind of lattice boson system with like pairwise hopping or something like that. Pairwise
hopping, like hopping like this. This is dipole conserving, and then we have local on-site interactions too. You can switch this, add this to the description. This is the model which we looked at. But again, the picture is very generic. Look at anything; it looks like this.
So one question from the previous slide. So you showed this stationary profile, which was tilted.
Yes.
So your total dipole moment is the charge and the dipole moment increases with system size, because the tilting is the non-zero dipole moment.
The tilting goes to zero in the thermodynamic limit for a fixed dipole moment.
Yeah. Okay. Thanks.
So you have to think about these things a little. Yeah. Good. But you see, you can introduce quantum effects either. We also did exact diagonalization on small systems. You see this fourth root and so on. So it's universal. It should come up everywhere when you, as long as you have a conserving approximation, which really conserves charge and dipole moment. So this is set here. And maybe also, I mean, this is not kind of, you might think maybe this is a bit esoteric what I'm talking about, but actually it's pretty easy to realize a system with charge and dipole conservation. And this has been done in Wasim Bakker's group, actually also last year. There's a lot happened last year. So what they did is that they took a two-dimensional Bose-Hubbard model, Fermi-Hubbard model, and tilted it. It's a quantum gas quantum gas microscope. It's a system of ultra-cold atoms, which is very well isolated from the environment. So this means that energy is conserved. But when you tilt, then the particles can't hop down the root, right? Because that would not conserve energy. So you have to have precisely these correlated hops in order to conserve energy. You get the delta, gain delta going to the right, and pay delta by going to the left. And then energy is conserved. And this is precisely here illustrated in this pictorial process. So in this tilted to the Hubbard model, there is an emergent dipole moment conservation. And when we look now at the, and what they did in the experiment is they looked at the decay of density waves, and they looked at this dynamical exponent. They called it alpha. Sorry, I called it Z previously because Z is usually very standard notation in the literature. But here, just replace Z by alpha, then you have the same thing. And And what they found is essentially that at large enough tilts, they did find indeed the set equal to 4 due to this emergent dipole conservation in their system. So this is an application of our fracton field theory, fracton hydrodynamics, if you want, here. So you see it also experimentally where quantum effects are fully taken into account.
So yeah, can I?
Please.
So what is the x-axis? Sorry, what is the x-axis on this figure? Maybe you mentioned it, but
this axis, this is the tilt strength. Yeah. So at strong tilt, they see it in their finite size system that subdiffusion emerges. Actually, it's not quite clear what happens at very weak tilts. My suspicion would have been that actually you should still see set equal to 4. We are simulating this at the moment also with some approach to understand this a bit better. If the system is large enough, I think you should see set equal to 4 throughout. But here it may just be that due to finite system sizes and times what they had, that they can't see that. But maybe I'm wrong here. This is a bit speculative. I don't know. Because of course,
in the effective model, this is like a linear potential in one or both directions.
In one direction here, but it doesn't matter, no, because you have dipole moment conservation in this direction, and they measure transport in this direction, so that's all what matters. In a one-dimensional system, this has been investigated in Emanuel Bloch's group. These 2 papers here. There it's more tricky. There they don't relax because of this fragmentation business. But the 2-dimensional problem is very good for us because it's relaxing and it has dipole moment conservation. It's precisely what I want to have, to see this hydro. This is in Wasim Bakker's work here. Guardado, Sanchez, et al. Okay, good. So that's a firm ground. There's interesting hydrodynamics here emerging at late times. You will see subdiffusion coming from these constraints. Classical effect. It's just a classical effect. So next question, which I would like to ask is what is going on with operator dynamics in the system, right? To touch upon what I called universal pieces of quantum evolution in the very introduction of this talk. So there is one way of measuring operator dynamics, but let me just pictorially tell you what I mean here. Take 2 operators which are compact in space, so O1 and O2, and evolve one of them in time. So initially at short times, they are not overlapping, so their commutation is essentially 0. At late times, they start to overlap because, you know, due to the time evolution and Baker-Campbell-Hausdorff and all the stuff, the operator is just spreading out in space. And the commutator will be non-equal to 0. When I take now an expectation value, this would be similar to this density-density correlation, then these phases cancel out because there's a plus, a minus phase, and so on, it just goes away. But when you take this absolute value of this object, or the absolute value square even, then you measure precisely this operator spreading, and this is what goes under the name of out-of-time ordered correlators. This is because when you take the square of it, there are correlation functions which are not time ordered in this expression, but maybe this is just maybe terminology. Yeah, there has been very nice work by Adam Nahum and also Kurt van Keyserling and all, where they developed a hydrodynamical description of operator growth. So again, nothing quantum in here. Operator growth is a purely classical phenomenon at late times. The only place where quantumness enters is in the effective velocities, butterfly velocities and stuff like this. Okay, so this is the typical picture. We have ballistic spreading of information, and we can look at some OTOC. For instance, here I make a spin flip at position 2, and I measure then at different positions how the operator set X is evolving in time or something like this. Huh? And this is now what we want to do in our system. But as I said, since we can derive a hydrodynamical description of operator growth, we might as well use just cellular automaton to simulate the dynamics. And this is what we did here. This has been actually, yeah, I'm not sure whether Sarang was the first, but I mean, these papers are certainly kind of have hinted toward this possibility of using this trick essentially to study operator dynamics, given that there is an emergent operator hydrodynamics, if you want. So again, we use our gates, conserving P and Q, and classically simulate the OTOC. And it turns out, yeah, one can do the calculation in one line, but what it effectively amounts to is take one time evolution, measure how the excitation propagates through the system, measure just the set operator, and then take another time evolution, but with a flipped spin, with an X operator acting on 0. Evolve that, make the difference of the two, and take the square. And this is precisely, you can show by 2 lines of calculation, or maybe 1, that this is identical to this OTOC. Okay, so this is the thing what we have to measure, essentially. So we have to compare these 2 trajectories. And again, the time evolution here is done via just a classical automaton. So this M of t, sorry, this bracket should go a little bit to the left. This M of t is just obtained classically. And it captures the universal late time features. So it's good enough for us to derive our new hydrodynamics of operator growth. Questions?
I think I have a question. So in the previous slide, can you come back to the previous slide? Sorry.
Yes.
Okay. So here you define the OTOC as, like, in the beginning, there is a commutation relation is 0, and then with time, this OTOC is basically increasing. Therefore, you are just saying this ballistic move. But you say that this should be true because of the quantumness, right? Because operator 1 and operator 2 don't commute because of this just adding up this term extra. But you say that this is also true for the classical case. So
yeah, I can just write a gate structure. You know, it's just because you can think of this commutator coming from classically. When you think about random unitary circuits, each time when I act a gate, I spread information through the system. And now the question is, do I need to take the complete set of gates, essentially, or can I just take classically simulable gates? And the answer is, because it's an effective hydrodynamic description, which determines how the operators propagate, I can take an effective classical set of gates, classically simulable set of gates. And this is this automaton circuit gates, which I'm using. So they transfer, just to make sure that this is clear, they transfer, we try to depict this in the picture. They transfer a configuration of states, a Fock basis, a Fock state, into a new Fock state. Okay, but no superposition. And with that, they propagate through this. Perfect, thanks. Yeah, further questions? So now we can make a bit of a connection to the classic physics community, right? I can now look, I can now look at an individual trajectory of an OTOC, a snapshot, if you want. Quantum mechanically, I have a state psi averaging over many of these snapshots at once. I can't look at an individual one very easily. But when I do this classical evolution, I can just look at one random incarnation of my gates and look at how the OTOC looks like. And now it's interesting because we will have times where it propagates, but then there will be times where the operator is completely stuck. And this is the so-called what we call waiting time, or what is in general called waiting time. And this can be long. I mean, this is just a typical picture in the ergodic regime. This is not somewhere in the localized regime of my system. So I'm in this ergodic evolving regime with waiting times where the operator is stuck for, you see, this long, many sequences of gates. This is like thousands and thousands of gates, and depending on parameters, we can make that very, very long. So where does this come from? This comes from bottleneck physics, because if I have a region, by chance, that all my spins are pluses, blue particles, and I apply a spin flip here, X, a white particle, then it cannot move due to charge and dipole conservation. We know that the system is not localized. So on average, the picture does not look like that, but locally it can look like this. So how can the operator escape from such a region, knowing that the outside world is ergodic, but we have locally a non-ergodic spot? So we can derive a rare region argument for that. assume that we have a frozen region of length L, or 2L in that. Maybe this is not so important, right? So, I mean, this is roughly of length L, the gray spot. There, the density is above the critical density on average. If I make an operator excitation in there, it cannot escape because of charge and dipole conservation. But what can happen is this frozen region can be eaten up from outside, because the whole region cannot be stuck, because the average density is below the frozen density. But this is a notoriously slow process, because it takes only subdiffusively with z equal 4 slow. It takes long times. The time goes as L to the 4 until this region is frozen up, eaten up. And only once it's eaten up, the operator can escape. And this is precisely this picture which I showed you for this one snapshot. It's stuck, stuck, stuck. It waits, the operator waits until the frozen region is eaten up from outside. And once this happens, it's happy again and it can move out. Okay? So this is this relation between space and time, which is very slow. And now we can ask, I mean, it's very simple random walk argument. Assume you have a small, small frozen region. And now you can ask, what is the probability of the next region to be frozen again? And you can write this down as a biased random walk. And then you need to ask, what is the probability, I mean, when do you reach 0 again so that you're not frozen anymore in your region? When is the density below the critical density? And this is this probability of return of such a biased random walk. It's known from statistical physics. So it has this power law in front and then an exponential. And the point is the system sees that it's not quite critical, only on a length scale, which is proportional, or only where the density fluctuations, say, are proportional to 1 over square root of L, the scale where I'm looking at. When I'm looking at two small scales, it doesn't see that it's not critical. And when you plug this all in, you get a distribution of these frozen regions. And this can be checked easily numerically. I mean, this just comes out, right? Because it's all drastic. This distribution comes out. And now we can use the marginalization rule or conservation of probabilities to translate this probability distribution of lengths to a probability distribution of times. Okay. And this goes then with a power law and then a stretched exponential multiplied to it. Okay. And now things become interesting. We can check that now numerically, whether this theory which I'm proposing you is making sense. And indeed, we find the yellow curve is at the critical density. We find a nice power law, t to the minus 9 over 8. Looks good, I would say, over many decades. So this goes, because it's classical, we can do very nice simulations. Goes to late time. We can find long waiting times of 10 to the 9 gates. Nothing happens, but they occur with low probability, of course. And when we go a little bit away from the critical density, and we are always approaching the point from below, right? So I'm always talking ergodic to critical point regime. Then we see it looks like a power law of with a stretched exponential at some point. This is what you see here. Okay, but now what's the consequence of that? So that means we have now a probability distribution of waiting times. In the ergodic phase, it is cut off by a stretched exponential. So the waiting times ultimately are not allowed to matter, because whenever you have an exponential or stretched exponential cutoff of a probability distribution, it doesn't do anything, right? So we do get ballistic transport in that case. But at the critical point, the stretched exponential vanishes. And when you plug in the waiting time distribution, now still two scenarios can happen. Either it's relevant or it's irrelevant. And here it turns out that it's actually pretty flat distribution, just in case as that operator spread at the critical point, indeed, just as a slow power law in time with 1 over 8. Okay, this comes from this picture. So let me just summarize. We have 3 regimes: linear operator growth in the ergodic regime, and then we have a power law growth of operators at the critical point, and stuck operators in the stuck regime. Okay, that's not so very much surprising. But surprising is that we get this critical point which influences influences dynamics a bit around it too, because, you know, a stretched exponential on numerically accessible scales is not so a severe cutoff. So in some sense, when we look at the OTOC front, how it spreads, we see that it approaches a constant in the localized regime, this t to the 1/8 at the critical point. And away from it, it still looks not very ballistic. Yeah. But what really happens is it doesn't look ballistic until it realizes that the stretched exponential cuts off the weighting time distribution, and then it becomes ballistic again. But there's a large region around this critical point here where operator growth is strongly dominated from it. So let me put this into a dynamical phase diagram. We have 1/time on the y-axis, and we have the critical density on the x-axis. Okay, at the critical point, I get my power law. Okay, I get sub-ballistic operator growth. But it turns out that when I look at a certain slice in time, it looks as if I have a big fan of where my dynamics looks sub-ballistic, a slower power law. And only when you wait long enough, okay, so you see this, you have this huge crossover regime. It's a bit similar in some sense to a quantum critical point, where here 1/time is replaced by temperature. So the critical point has influence on the dynamical properties around it. Okay, this is just what we have here. Okay, so we have critically slow operator growth at the critical point. So what are the implications? We have a bound on the transport at this point too. So this is certainly larger than 8. Maybe it can be even exactly bound to 8, but we cannot with our techniques. Transport is more complicated. So we don't have an analytic theory for that. We can look at different out-of-time ordered correlators. The XX correlator, for instance, is bounded by the ZX operator. We can work this out. Johannes did a great job doing that. And the question is, of course, we have here one-dimensional fractonic systems. In some sense, what is the consequences for higher dimensional analogs? And we've looked at transport in such a system, a higher dimensional fractonic quantum system, but we don't know yet what the operator growth would be. I mean, is it influenced from this type of dynamics, yes or no? So this is an open question. Okay, so maybe, yeah, so just 2 seconds or 2 minutes maybe to put a bit this into perspective. So recently, many papers have appeared which study constrained quantum dynamics, okay? And the classes of systems is huge in some sense. So there are on the one hand, these dipole conserving systems, which I've discussed today, but on the other hand, there may be models which have kinematic constraints, like an XNOR constraint, a DJC constraint, or something like this. And people have looked at transport in various, in these systems. And now, I'm talking about not about the dipole conserving systems. They're special. They have been dealt with in some sense now. But these other types of systems which have these kinematic constraints in the Hamiltonian directly, is there the question which we had is there some unifying description of the dynamics in this system? Because it seems like so many different results in some sense, so many opportunities and possibilities to cook things up. So what we have identified is that many of these systems have an underlying charge pattern conservation. So for instance, I have here blue, red, blue, blue. And under time evolution of these Hamiltonians, this charge pattern, blue, red, blue, blue, is always conserved. And once you have that, transport can be mapped onto a classical diffusion problem, which is the tracer diffusion problem. Tracer diffusion is a tagged particle which diffuses through my system, which with a hardcore constraint, so it cannot hop over other particles. So if you have a look at this picture here, the blue particles always stays between the blacks, so it does never hop around it. So they're always 3 to the left and 3 to the right in our cartoon picture, at least if you did it right. Yeah, we did it correctly. Okay. Tracer diffusion is known. So tracer diffusion in classical system goes with Z = 4, subdiffusion again. And again, with that we can explain now different classes of models. So for instance, DJC, you know, has spin down, spin up, and hole. And the transport in this system can be really straightforwardly mapped onto tracer diffusion. and we can get the dynamical exponents for an integrable version of the DJC model or for a random unitary circuit model of the DJC model. They are different because what you get is, due to tracer, you get a factor of 2 in your set. Integrable models are ballistic, Z is equal to 1. Tracer gives you Z equal to 1 times 2 is 2. Random systems are diffusive. Tracer gives you another factor of 2, gives you Z equal 4, strong subdiffusion, okay? But the point is, what I want to make just as last statement, we can also compute the values of the diffusion constants out of this tracer diffusion mapping. So this is what Johannes is currently wrapping up. So it's a bit of a different story, but I think it unifies at least a couple of models which are out there in this constrained quantum dynamics. Okay, but with that, let me close and come back to our ultimate goal of this talk, which is looking at fracton or dipole conserving models. And there we have this interesting type of subdiffusive transport and also very interesting operator growth. Thanks.
All right. Thank you very much for this great talk. So we can stop the recording, maybe.